Hello, my dear students of Benguet State University. Welcome to our online class. I am your teacher, Jan Lasea.
Ladies and gentlemen, a blessed day to everyone. This is my 8th lecture in our subject, IT 112, Discrete Mathematics. In my previous lecture, I explained the application of logic, which is combinatorial circuits. You learn logic gates, the implication or conditional proposition, and by conditional proposition, connectives or logic operators. Today we are going to learn propositional equivalences. Tautology is a compound proposition that it is always true, no matter what the truth values of the propositions that occur in it. A contradiction is the opposite of tautology. It is a compound proposition that it is always false, no matter what the truth values of the propositions that occur as well. Contingency is a proposition that is neither a tautology nor a contradiction. Logical equivalent, symbolizes by the equal symbol, it is a compound propositions that have the same truth values in all possible cases. Logical equivalences. The logical equivalences have similarity in algebra, which is the properties of real numbers. The commutative laws state that P or Q is equal to Q or P. Another is that P and Q is equal to Q and P. The associative laws state that the grouping of terms and literals by parentheses, for example, quantity P or Q or R is equal to P or quantity Q or R. Another, quantity P or Q or R is equal to Q or quantity P or R. Another is quantity P and Q and R is equal to P and quantity Q and R. Another is that quantity P and Q and R is equal to or equivalent to Q and quantity P and Q. Distributive laws state that P or quantity Q and R is equal to quantity P or Q and quantity P or R. Another is P and quantity Q or R is equal to quantity P and Q or quantity P and R. This distributive laws is similar in algebra's distributive property. We distribute that P among the terms, for example, P or Q. The connective end between Q and R will be the main connector, and then if we distribute P again, P or R, it becomes now quantity P or R. The other one, if we distribute P among the laterals Q or R, it becomes P and Q, quantity P and Q. The connective or becomes the main connector, so we write or, and then finally we distribute P and R, and it becomes quantity P and R. The De Morgan's laws state that not of the quantity P and Q is equal to not of P or not of Q. Another is not of the quantity P or Q is equal to not of P and not of Q. I already discussed and explained these De Morgan's laws in my previous lecture. Absorption laws state that P or quantity P and Q is equivalent to P. Another is P and quantity P or Q is equivalent or equal to P. The double negation law or involution law states that not of the quantity not of P is equal to P. This is similar in algebra of multiplying a negative to another negative that the product is positive sign. Tautology states that P or not of P is equivalent to 1 or true. It is always true or 1 no matter what the truth values of P. Contradiction states that P and not of P is equal to 0. It is always false or 0 no matter what the truth values of P. Identity laws state that P and 1 is equal to P. Another is P or 0 is equal to P. Domination laws state that P or 1 is equal to 1. Another is P and 0 is equal to 0. Idempotent laws state that P or P is equal to P and P and P is equal to P. Contrapositive states that if P then Q is equal to, if not of Q then not of P. Other logical equivalences. Letter A. If P then Q is equivalent to not of P or Q. Letter B. If not of P then Q is equivalent to P or Q. Letter C. Not of the quantity if P then not of Q is equal to P and Q. Letter D. If not of P then quantity if P then Q is equal to 1. A tautology. Letter E. P if and only if Q is equal to if P then Q and if Q then P. Letter F. Not of the quantity if P then Q is equivalent to P and not of Q. Letter G. Not of the quantity P if and only if Q is equal to P if and only if not of Q. Letter H. Not of the quantity P exclusive or Q is equivalent to P if and only if Q. And letter I. Not of the quantity P exclusive or Q is equal to not of P and not of Q or P and Q. You need to memorize or familiarize the different logical equivalences. To apply the different logical equivalences, let us solve an example problem. Example number 1. Simplify the Boolean expression below to a minimum number of literals. Not of the quantity P or Q is not of the quantity P or Q or quantity not of P and Q. To simplify this Boolean expression, we first examine the Boolean expression from left to right. Now, we can see that this term, not of the quantity P or Q, we can apply De Morgan's law. So if we apply De Morgan's law, not of P becomes not of P, not of or becomes N, not of Q becomes not of Q. And then we write the rest of those literals. We write or and then quantity P not of P and Q. Next, we examine again from left to right. We can now find out that we can apply distributive laws. We can see or observe that not of P is present between the two terms. We have not of P here and not of P here. And then it is connected by the main logical connector OR. Therefore, we can apply the distributive laws. So, we remove not of P from this term and it becomes not of P. And then we get the N. And then we combine not of Q or Q. And if we check if this not of P and quantity not of Q or Q is the same as this. Applying distributive laws, not of P and not of Q becomes quantity not of P and not of Q. We get that OR and it becomes the main connector. We distribute not of P and Q, it becomes quantity not of P and Q. That's why it is a distributive laws. We again examine the Boolean expression from left to right. We can observe that this quantity not of Q or Q is a tautology. Not of Q or Q becomes 1 or true. So we write now not of P and 1. Finally, we apply the identity laws. Not of P and 1 becomes not of P. So therefore, the Boolean expression not of the quantity P or Q or not of P and Q becomes a not of P, as reducing the Boolean expression to a minimum number of literals. And not of P is the equivalent of this Boolean expression, and that is the answer. Example number 2. Simplify the Boolean expression below to a minimum number of literals. Quantity P or Q and not of P. To simplify this Boolean expression, we first examine the Boolean expression from left to right. And then we can apply now distributive laws. We will going to distribute not of P among the terms P or Q. So if we distribute, not of P and P becomes quantity not of P and P. We get the OR as the main connector, and then we distribute again, not of P and Q becomes quantity not of P and Q. This distributive laws is similar in algebra distributive properties. If we distribute a term among the literals that has a multiplication operator. Come next, we can observe that this quantity not of P and P is a contradiction, and it is always false. Therefore, it becomes 0. And then we copy the rest of the terms. We write OR quantity not of P and Q. And then we simplify the Boolean expression that we observe and examine from left to right. And then we can now apply identity laws, 0 or quantity not of P and Q. Applying identity laws, it becomes now not of P and Q. And that is the answer. Example number 3. Simplify the Boolean expression below to a minimum number of literals. Not of the quantity P or quantity not of P and Q. To simplify this Boolean expression, we first examine the Boolean expression from left to right. And then we can apply now De Morgan's laws. So if we apply the De Morgan's laws, not of P becomes not of P. Not of OR becomes N. Not of the quantity not of P and Q becomes not of the quantity not of P and Q. Next, we examine the Boolean expression from left to right. Again, we can now observe that we can apply De Morgan's laws in this expression, not of the quantity, not of P and Q. So if we apply De Morgan's laws, so not of P becomes positive P, applying also the double negation law. Not of N becomes OR, and not of Q, not of Q. And then we write the remaining terms, not of P, N. And then after that, we can distribute this not of P among the terms within this group or parentheses. So applying distributive laws, not of P and P becomes quantity not of P and P. We copy the OR and it becomes now the main connector. We distribute again, not of P and not of Q becomes quantity not of P and not of Q. Next, we examine the Boolean expression from left to right. We observe that this quantity not of P or P is a contradiction. So it becomes 0. And then the rest we copy 0 or quantity not of P and not of Q. We can apply identity laws. So this expression becomes now not of P and not of Q. And that is the answer. Example number 4. Simplify the Boolean expression below to a minimum number of literals. If quantity P and Q, then quantity P or Q. To simplify this Boolean expression, we examine the Boolean expression from left to right. And then we can apply the other logical equivalences. Letter A, this other logical equivalence. If P then Q is equivalent to not of P or Q. Applying now this logical equivalence, it becomes now not of the quantity P and Q. That conditional proposition becomes now an OR, and then we copy quantity P or Q. Next, we examine the Boolean expression from left to right, and we can see that this term, we can apply the De Morgan's laws. So applying the De Morgan's laws, not of P becomes not of P. Not of N becomes OR. Not of Q becomes not of Q. And then the rest, we copy or quantity P or Q. Next, since all the terms or the Boolean expression has a uniform connector which is OR, we can apply associative laws. We can group not of P or P and then enclose it with parentheses, and we can group not of Q or Q and then enclose it with parentheses. And the reason why that I group them, because they are tautology. So not of P or P becomes 1, not of Q or Q becomes 1, and then 1 or 1 is a logical 1. The logical or truth value of 1 or 1 is 1. And that is the answer. So the Boolean expression, if quantity P and Q, then quantity P or Q is equal to 1 is a tautology. I posted your 8th assignment in our Google Classroom. Please answer and accomplish it.
That ends our topic for today. I hope you have learned in my class. Thank you for watching. Carry on until tomorrow. God bless us.